All right. Of course, if anyone has any questions, please feel free to text them into the lecture text or unmute yourself and speak up anytime. So to pick up where we left off last week, we finished talking about the first two types of pericyclic reactions, the Diels-Alder reaction and other cycloadditions, as well as the electrocyclic reactions. And so the third type of pericyclic reaction that's discussed in chapter 17 is the sigmatropic rearrangement. The theme here is the same as the other pericyclic reactions, where the electrons shift around in a circle. The difference is that the total number of pi electrons in sigma, or pi bonds and sigma bonds, isn't changing. So it's really just a rearrangement. In this particular simple example, if you shift the electrons around according to the arrows could also go this way. We give you the same product. So you can have the arrows go clockwise or counterclockwise. That looks really cluttered, so I'm going to get rid of it. The product that would be produced would be really identical to the reactant. So in this structure, it could be constantly happening back and forth. The equilibrium would equally favor both sides because both sides are identical. And so that wouldn't really be much of a point in describing that reaction if the product it produces isn't different from the reactant. It's just a pancaked, flipped over version of it. But there are other instances where the reaction actually changes the structure. So we want to talk about this in a little bit more detail. So the notation focuses on the number of atoms, not necessarily carbons, but often they are, on either side of the sigma bond that breaks and forms. Right, so there's no change in the number of sigma bonds, but one of these sigma bonds is breaking and becoming a pi bond, while one of these pi bonds is shifting over and becoming a sigma bond. So if we draw the transition state and we use a dotted line to show each bond that's breaking and each bond that's forming, and not just the sigma bonds, but also here I have a pi bond forming, here I have a pi bond breaking, here I have a pi bond breaking and shifting over there, forming one there. That gives me dotted lines all the way around. So that's the key feature of a pericyclic reaction. But if I specifically focus on the sigma bonds that are breaking and forming and count the number of atoms on either side of that, right? So here are my two sigma bonds. I've got 3 atoms on this side and 3 atoms on this side. That's what gives the notation in front of the name sigmatropic rearrangement. So the type of sigmatropic rearrangement is noted by giving you the number of atoms on either side of the 2 sigma bonds that are breaking and forming. So here's an example of a 1,5 sigmatropic rearrangement. Where's the sigma bond that's breaking? So I do the same thing. I have the electrons shift around in a circle. I can draw the transition state. This sigma bond here is breaking. The electrons are shifting over and forming a sigma bond right there. So there's one atom on this side of the 2 sigma bonds, and then there's 1, 2, 3, 4, 5 on the other side. So that's why it's a 1,5 sigmatropic rearrangement. So in this case, which side would the equilibrium favor? So these transition states are somewhat stabilized by the fact that they have a circular motion of the electrons and that the dotted line extends all the way around the ring. But that's more of a kinetic consideration, right? If we're interested in how stable is the transition state versus the reactants and how much energy do you need to put in to make the products, that's a kinetic question. But if we're asking a thermodynamic question, which is when this occurs and it reaches equilibrium, am I going to get more reactants or products? Then I have to look at the stability and the entropy of the reactants versus the products. So in terms of entropy, there's 1 mole on both sides. It's not a ring really on either side. There's an equal number of pi bonds. So there's probably about as much rotational freedom that's constricted by the pi bonds over here as there is over here. So the entropy looks very similar, so we would have to really judge based on the enthalpy or the stability, and that's mostly going to be based on how substituted the carbon-carbon bonds are. Right? So if I look at how many of these positions of the sp2 hybridized carbons have hydrogens bonded on one side versus carbons, and then compare that to the other side, if it's very similar, where both sides have 4 out of the 8 positions occupied by hydrogens and the other 4 occupied by carbons, that's going to be a very similar situation. It's going to be really hard to judge which side is more stable than the other, and so probably will produce an equilibrium that would favor both sides pretty equally. However, here we can see that when the equilibrium is reached, we get significantly more of one substance than the other. So these are the kind of things we'll be asking you to look for. If you're looking at spontaneity, which is thermodynamics, you're just comparing the reactants versus the products, entropy and enthalpy. So the Cope rearrangement is named after some dude, and it's specifically a 3,3 sigmatropic reaction where all 6 atoms in the ring are carbon atoms. So in the Cope rearrangement, I've got 6 carbons, the electrons flow around, I get a different 6-carbon ring. There may be groups more than one methyl group. There may be other R groups bonded here. There may be other atoms attached. I could have an oxygen here. The key is that the 6 atoms in the that form the circular movement of electrons where bonds break and form, those 6 atoms are all carbons. So if you shift the electrons around, you get the double bonds over here. How can we explain why one side's more stable than the other? Well, what we're just talking about is looking at how many of the positions that are sp2 have hydrogens bonded versus carbons. And over here, because of this methyl group creating now a substitution on the sp2 hybridized carbon, there's 1, 2, 3, 4, 5 hydrogens bonded to my sp2 hybridized carbons, and 1, 2, 3 carbons. Versus over here, where I've got 3, 4, 5, 6 hydrogens bonded on the sp2 hybridized carbons, and only 1, 2 carbons. So that slightly more substituted pi bond, we've been seeing that theme come up a number of times, is going to make this structure a little bit more stable, and that accounts for it being the major substance once the equilibrium is reached. So when it comes to sigmatropic rearrangements, if all the atoms are carbons, it's called a Cope reaction. And in a Cope reaction, the main thing you look for to determine which side is favored is how substituted those pi bonds are with other carbon groups. Very similar reaction, different variation on the sigmatropic rearrangement, named after a different dude. If oxygen is one of the atoms in the 6 atoms involved in the electron shifting, that's a Claisen rearrangement. It's still a 3-3. So between this sigma bond breaking and this one over here forming, there's 1, 2, 3 atoms up here and 1, 2, 3 atoms down there. So we separate where the sigma bond's breaking and forming. Look how many atoms are on both sides. If it's 3, 3, and one of the atoms is an oxygen, that's a Claisen rearrangement. And so here, what we notice is the difference in which side is favored in equilibrium doesn't depend on how substituted the carbon-carbon bonds are, where the carbon-oxygen bonds are. Because here I've got this pi bond has one, it's not a carbon, but one group bonded to it that's not a hydrogen, and one over here that's not a hydrogen, And the same thing over here. So these two sides, the pi bonds are roughly equally substituted with non-hydrogens. But there is a difference because the CO double bond is especially stable. And we've seen that before. We've seen that before when we were talking about enols and that enols rearrangement. So if you recall, last semester, near the end of the semester, we did a reaction that converted an alkyne into an enol. So if you do a hydration across an alkyne, whether it be a Markovnikov like this one is or anti-Markovnikov, the conditions end up being different. But a Markovnikov hydration across an alkyne, you could accomplish that with some sulfuric acid and mercury sulfate as a catalyst. That would produce an enol, and then we said that undergoes a couple steps in its mechanism to produce an equilibrium where the hydrogen and the pi bond will shift. So instead of the oxygen bond to the hydrogen will end up bonded down here. And that will pretty much go exclusively to one side. The reverse reaction there, the equilibrium there is pretty much product favored. So there are a couple instances we'll see later in the semester where the enol is more stable than the ketone, but generally a C-C double bond is not nearly as stable as a CO double bond. And so that same theme here governs this equilibrium. When you have a Claisen rearrangement, you want to recognize that because a CO double bond is significantly more stable than a CC double bond, that helps that shift toward the side with the carbonyl versus the side with the alkene. Here's an example of a couple pericyclic reactions that occur in biology. So you're probably aware if you go outside, like on a nice sunny day like today, soak up a little sun. The sun can initiate biosynthesis of vitamin D, and everyone needs vitamin D, and the main source of getting that is from the sun for most people. So the energy from the sun provides the energy to cause an electrocyclic ring opening on this steroid that is naturally produced in the body. So this would be present in your skin, and the sunlight would hit your skin, and it would cause this pericyclic reaction, specifically an electrocyclic ring opening. So following those electrons, and again, we could push them around a circle either clockwise or counterclockwise to get the same product either way. That produces this intermediate, which then undergoes a sigmatropic rearrangement, and it's a 1,7. How do I know that? Well, this is a sigma bond that's breaking, right? The other bonds here that are shifting are all pi bonds. This arrow looks like it's starting on a sigma bond, but it's really the pi bonds that are shifting over. So I have one sigma bond breaking, and then when that shifts over here, it's going to make a new bond between this carbon and this hydrogen. So looking at the atoms on this side of where the two sigma bonds are breaking and forming, I have one atom. And on the other side, I've got 1, 2, 3, 4, 5, 6, 7. So that's why it's a 1,7 sigmatropic rearrangement. So that occurs after the ring opening, and after that rearrangement, you get vitamin D. This is the structure of vitamin D. And so that is an important reaction that occurs. That's why you need sunlight to produce vitamin D naturally in your body. All right, so the last section here of chapter 17 is about UV-vis spectroscopy. So last semester we talked about IR and NMR and mass spec. And we didn't really talk about UV because UV isn't really relevant unless your compounds have conjugated alkanes. And so now that we're talking about conjugated alkenes, now is the time to discuss this type of spectroscopy. So we were saying, if I have an alkene like butadiene, oops, this should be a double bond there, and I look at the p orbitals on each one of those carbons, right? So what we've been saying here about conjugated pi systems is the p orbital overlap doesn't just occur between atoms where there's a pi bond, right? So I can have a pi bond there, and I can have one here. The construct of interference here makes a pi bond. The construct of interference here makes a pi bond. But even though there's only a single bond between these two carbons, if they have the same wave sign and they overlap, that will also create construct of interference. So construct of interference all the way across the top and all the way across the bottom will create molecular orbitals with no destructive interference. And the pi cloud will not have any nodes other than the node that's in the plane of the carbons. And so that really stabilizes the electrons. So the most stabilized electrons, the ones in the molecular orbital with no nodes, are not involved in UV-vis spectroscopy. What's happening here is the highest energy occupied orbital, which will be the next one up, which would have one node, right? So here we have a node because there's constructive interference here, but then there's destructive interference between the right half of the molecule and the left half of the molecule. So this is a little bit less stable because the electrons can't get in this area where the constructive interference occurs. But since there are 4 pi electrons, both of these orbitals will be occupied. The next orbital up, which would typically be unoccupied, which is why it's the LUMO, the lowest energy unoccupied molecular orbital, that one would have a couple nodes. And so now there's more destructive interference than there is constructive interference. And so we talked about this before. There'd be some constructive interference here for the electrons to exist in the area between these nuclei, but the destructive interference occurs in more areas than the constructive interference, so that's less stable. So there's a defined energy difference between having an electron in this orbital versus having it in this orbital, and that energy difference is what UV-vis spectroscopy measures. So what happens is you put your sample in the instrument, the light hits it, some wavelength of light in the UV visible range, somewhere in that range, that wavelength of light is going to match this energy difference. And when that specific wavelength of light hits this electron, it's going to pop it up. So we're using light to pop the electron up from what was the old HOMO now to what was the old LUMO. And now this becomes the HOMO, and this becomes the LUMO. So we're measuring this quantity of energy by measuring what wavelength of light corresponding to that quantity of energy is absorbed when the electron is promoted. What happens to the electron after it's excited or promoted up? Well, then it would relax back down and release energy in the surroundings. Sometimes that energy is released as kinetic energy, which is more difficult to measure. So in this particular type of spectroscopy, we're not measuring the light that's emitted when the electron relaxes back down. We're measuring the light that's absorbed. In order to measure light that's absorbed, you have to have the instrument hold your sample, usually like in a little cuvette or something, which I can't draw very well, but your sample would be in here, and you'd have the light passing through it, but you'd have all these different wavelengths. You'd have some shorter wavelengths, you'd have some longer wavelengths, and if the molecule in there has a specific energy gap between its HOMO and LUMO that matches one of these wavelengths, well then the other wavelengths will make it through, but the one that's absorbed won't come out the other side. So the instrument knows what wavelengths it shot through the sample, and then it reads what wavelengths made it out. And it subtracts to find out which wavelength was absorbed by that sample. So in order to do this properly, though, the light is actually split into two beams. So you have it go through your cuvette with your sample in there, and you have the same wavelengths going through a cuvette that has just the solvent. Because the solvent, it may absorb some UV light. If the solvent absorbs some light and I don't see it coming out the other side, well, it also wouldn't make it out the other side when I have my unknown or compound dissolved in the solvent. So whatever light the solvent absorbs, we need to use that as a control. It's a negative control. So by measuring what wavelengths of light the solvent absorbs, when we see those absorbed when our other sample is there, dissolved in the solvent, we know that the sample is not absorbing those, it was the solvent that was absorbed. So we're using this as a control, and it's detecting the light that comes through for both of these. So only light that gets absorbed by the analyte that's dissolved in the solvent, that doesn't come out the other side, the machine can tell us what wavelengths of light don't come out, specifically because they're absorbed by the solute rather than the solvent. So that's the purpose of having the solvent there as well. So it measures the intensity of the light that passes through. It compares both of them. Any light that passed through the solvent but didn't pass through up here with the unknown or analyte dissolved in the solvent, that must have been absorbed by the analyte. And then it gives a readout of that. So if I dissolve this in some solvent, and I just look at the wavelengths of light that are absorbed by this compound that are not absorbed also by the solvent, I get this curve. And this shows at about 217 nanometers, that was the maximum amount of energy that was absorbed by this compound. And so that correlates, the energy of that correlates to the energy of the HOMO to LUMO gap for the electron. So that means this must be the wavelength of light that was absorbed to cause that electron to jump up to the next energy level. So let's take a look at what happens when you extend the conjugation. So what we were saying before is if I have a fewer number of orbitals overlapping, I get a smaller number of molecular orbitals, right? Every orbital that's overlapping goes away and I get an equal number of molecular orbitals resulting from that overlap. So if I have 4 p orbitals overlapping, I get 4 molecular orbitals. And the energy gap between the HOMO and the LUMO is relatively large. If I make more p orbitals overlap, 6 of them, I'll get 6 molecular orbitals. So now I have 2, 4, 6 pi electrons, 3 pi bonds, 6 pi electrons. So those 6 pi electrons go in the lowest energy ones. And in order to excite that up, the energy of the light doesn't have to be as high. So it's a longer wavelength. Right? Remember, the longer wavelength has less energy than a shorter wavelength because the shorter wavelength carries more packets and has a higher frequency with which the energy hits the sample. So if I have a smaller energy gap, a longer wavelength will be the one that's absorbed to cause that electron to get promoted. And if I extend the conjugation even more, I see an even longer wavelength because the energy gap is even smaller. So basically you're fitting more energy levels in when I have more orbitals overlapping and a greater number of pi electrons in there. And that means the specific energy gap between the HOMO and the LUMO is going to be relatively small. So you can use this technique to figure out how much conjugation there is in your sample. If there's no conjugation, and maybe I only have 1 pi bond, well then the energy gap between the bonding molecular orbital and the anti-bonding molecular orbital is going to be very large. And the wavelength is going to be below the wavelengths that are used in UV-vis spectroscopy. They usually range from about 200 to 800 nanometers. It's a small part of the light or electromagnetic spectrum, but those are the wavelengths that are usually shot through the sample in a UV-vis instrument. So if you only have one pi bond and you don't have any conjugation, it's going to be below that and you're not going to see any absorbance. So typically you only see absorbance in UV-vis when you have at least some degree of conjugation. That's required to increase the wavelength or lower the energy enough between the HOMO and the LUMO to see an absorbance in this range. So you can see going from 2 pi bonds conjugated to 3 to 4, it doesn't really increase the wavelength that much. And so none of these compounds are colored. The colored light doesn't usually occur until you get above about 400 nanometers. 400 to 800, that's the colored part of the spectrum. So what would be required to make a molecule that actually absorbed colored light would be more conjugation. And that's what we see in chromophores or conjugated pi systems that have a lot more pi bonds. So this one still wouldn't qualify, but this is just to point out what the term chromophore means. If I have an extended pi system that's conjugated and all the p orbitals on all those atoms are all overlapping side by side, the more p orbitals there are, the more energy levels there will be, and the smaller the gap will be between them. And so if it's a small energy gap between the HOMO, and exciting one of those electrons from the HOMO up to the LUMO, then that's a higher higher or longer wavelength. This is the symbol for wavelength. And so, just looking at the experimental results of measuring a whole bunch of different conjugated systems with different numbers of p orbitals overlapping, Woodward and Pfizer put together a list of rules for what the wavelength should be. So we're not going to get into quite that level of detail, but I did want to point out a couple systems that do produce color, or I should say absorb color. And here are a couple examples of that. So lycopene is the chemical in tomatoes that's responsible for their red color. So this is this molecule is red. So this pi bond here and this one here are not in conjugation with the rest. But I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22 p orbitals all overlapping side by side. So there'd be 11 bonding molecular orbitals and 11 anti-bonding molecular orbitals. I didn't count, but there'd be 11 of each, so 22 total orbitals, which is probably more than I drew, but that means the gap between the HOMO and the LUMO is a very small gap. The energy required to excite an electron from the HOMO to LUMO would be quite small, and the wavelength for that would be relatively large. So if I see a red color, does that mean it's absorbing red light? The answer is no. Right? So you got to remember, if we're looking at light that's absorbed, the light that's absorbed is not reflected into your eyes. So when you see a red color, it's because the red is not absorbed, but the other color, like green, is absorbed. And that, you can think about the color wheel. So red and green are on opposite sides. So if the energy gap is absorbing a specific wavelength of light and your eyes are seeing red, it's because the green is absorbed. You're not seeing the green. When your eyes see all the colors at once, they can't distinguish between them. It just looks like colorless or white. When one color is absorbed and your eyes don't see that color, like if green is absorbed, then your eyes see red. So this specific molecule, lycopene, absorbs green light specifically because the energy gap between its HOMO and LUMO is a quantity of energy equal to the energy of the energy in green light. This molecule here is beta carotene. You can see it also has an extended pi system. That includes 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 20, 21, 22. So it also has 22 p orbitals overlapping side by side. And so that's why its color is so similar. Orange and red are very similar on the color wheel, right next to one another. But the exact structure has also some impact on the energy gap. So we can also use UV-vis spectroscopy to identify a substance. You've made some dye, you want to identify it has the correct structure. You know it's supposed to have a very specific quantity of energy gap between the HOMO and LUMO. You can put that in the instrument and measure the energy gap by measuring what color of UV-vis light it absorbs and identify that you have that substance present. If you want to get rid of the color in some compound, if it has color due to this extended conjugation that we've been talking about, one way to do that is to add something across one of the pi bonds. So when you bleach a stain, you're not really removing the stain. You're really actually just simply adding across a pi bond. That's what bleach does. It does an addition reaction. So now you break this long range conjugation up, right? There was p orbitals on all of these. And what we just saw on the last slide is it takes about 20 or so p orbitals all overlapping in like a chain to make enough energy level so that they're so close together that the HOMO and LUMO energy gap is small enough for it to absorb colored light. So if you break that and now you have a couple smaller systems, well then this system of p orbitals overlapping will probably only absorb UV light. And this system over here is also smaller, and so it will probably also only absorb UV light. So by breaking up the extended system, you now create two separate systems because now you have sp3 hybridized carbons in between, and so this, this system of p orbitals can't overlap with that one, and so this one will have much larger gaps, and this one will have larger gaps, and so you lose the small gaps that are responsible for absorbing colored light if you lose the extended conjugation, the long-range conjugation that specifically is responsible for absorbing colored light. So does the bleach actually remove the stain? No. It just undergoes a chemical change that causes the molecules that were part of that stain to not absorb light anymore, so they don't appear colored anymore. All right, that's it for chapter 17. Any questions on anything from chapter 17? Amy, your rainbow's gone? What rainbow? The bleach destroyed your rainbow. Oh, I'm sorry. Yeah, you don't want to get bleach on anything that has color if you want the color to remain. Yeah, they'll definitely break up those long-range pi systems and they'll lose their color. So that's obviously why you wouldn't want to use bleach unless you actually have a white material that you just want to remove all the color from altogether, because it doesn't wash away the stain. It just decolorizes it. All right, so in chapter 18, we're going to talk about aromatic compounds. And we've seen some aromatic compounds already throughout the last semester and this semester. But we're going to focus specifically on aromatic compounds in this chapter, and then the reactions that they undergo in the next chapter. So the simplest aromatic compound is benzene, and we're going to talk about what makes benzene aromatic and what the exact criteria for that are. I think probably on Wednesday. But one of the main things you want to definitely think about aromatic compounds is that they're fully conjugated in a ring. So in aromatic compounds, you need a ring and it has to be fully conjugated. That is the minimum requirement for something to be aromatic. There are other criteria as well that we'll see in a future lecture. But benzene is fully conjugated. It's got p orbitals on every carbon. So the p orbitals overlap all the way across the top and all the way around the bottom. And all of that overlap creates molecular orbitals. There's a HOMO and a LUMO and an energy gap. And so you could also use ultraviolet light to detect the presence of benzene because of the excitation that light would cause for its HOMO electron to be moved up to the lowest occupied, unoccupied orbital, or the LUMO. You can also make derivatives of benzene, which would be created by substituting one of the hydrogens on a benzene ring, of which there are 6 all the way around. Substitute one or more of those hydrogens for some other group. So you could put a methyl group there, you could put a couple methyl groups on there, you could put oxygen, nitrogen, all kinds of different atoms can be substituted onto a benzene ring to make a derivative of benzene. So we're going to talk about all of that in due time as we go through. A lot of these compounds are fragrant, which is why they got their name aromatic, but that was before much of the structural details were known. So it's not correct to think that all aromatic compounds actually smell, or even that all of them smell good. Many of them smell terrible, and many of them don't have any smell at all. And so whether or not it has a smell is not a criteria to judge whether it's aromatic. So we're going to talk about what features it needs to have beyond being fully conjugated for it to be an aromatic ring. There are lots of different pharmaceuticals that aromatic rings appear in. So here's one. Actually, this is an aromatic ring as well. The nitrogen is sp2. It has a p orbital, and those orbitals overlap all the way around. Here I have an aromatic ring. Here I have one. This one is not aromatic. If any atom in the ring, all it takes is one, is sp3, it can't be an aromatic ring. So if I have 4 sp3 carbons, definitely not aromatic. It has to be sp2 all the way around. Coal is mostly composed of fused aromatic rings. So here I've got one. It's fused to one over here. This one's fused to more. And then there are also alkyl chains and other functional groups because coal is made, fairly chaotically under the ground with a lot of pressure. But it's these aromatic rings that are fused together. All those pi bonds, when broken up and converted into CO2 and water, that releases a lot of energy because the electrons are much more stable in the products of combustion than they are in hydrocarbons. And so that releases a lot of energy that, for a lot of people provides the electricity for the home and stuff like that. So you should be aware, at least in a general sense, what the structure of coal looks like. And, so just so you know, these bonds, this would obviously be a nanoscopic chunk of coal. It's going to be connected and branched out in all these different directions into, three-dimensional kind of polymer-like structure with all these fused rings joining together and connected through alkyl groups that are, branched or straight chains. There's a lot of variety in the structure of coal. So we're going to be focusing on some relatively straightforward, simple aromatic compounds. And if you just have the simplest 6-membered ring that's fully conjugated, that'd just be benzene. If you put something on the benzene as a substituent, usually you're going to consider benzene to be the parent, and whatever's connected there will be the substituent. So if it's a chlorine, it would be a chlorobenzene. If it's a nitro group, it'd be nitrobenzene. If it's a 2-carbon, which is eth, as a substituent, that'd be ethyl. That would be ethylbenzene if there's an ethyl group connected to a benzene. However, a lot of times the parent name won't be benzene. If there's a methyl group connected to the benzene, you can call this methylbenzene. But you really won't pretty much ever see anyone call it that because that is not the most common name for it. So this slide here, you definitely want to become friends with so that you can recognize when you have to name a structure. If there's a benzene ring that's specifically connected to one of these groupings of atoms, then you would not expect to see it called methylbenzene or something benzene, because these specific groupings of atoms are actually combined with the benzene ring to create a new parent name. So instead of saying hydroxybenzene or methoxybenzene or carboxylic acid benzene or something like that, that becomes incorporated into the parent chain, and we don't use the name benzene, we just use one of these specific names for those groupings. So toluene implies a benzene ring connected to a methyl group, and anisole implies a benzene ring connected to a methoxy group. And so that becomes the parent. So then if there are other things attached, like let's say there were an ethyl group here, if I want to use this name as my parent, which I should, that includes all of this. And it also requires that when you number the ring, the first carbon is the carbon that the group is attached to that's part of the parent. And so the word anisole implies there's a methoxy group connected to the ring. That's all part of my parent name, so whatever carbon that methoxy group's connected to has to be carbon 1, and then I can number around to give the other groups the lowest number possible. So this would be 3-ethyl anisole. All right, so let's look at some more examples. Actually, before we do that, I just want to also point out, if you have a carbon group that's longer than 6 carbons, you could also name that as the parent chain, since now it has more carbons than the benzene. And if I name that as my parent chain, 7 carbons is heptane. And so now I have to name this as a substituent. So if you have a benzene ring that's not your parent chain, but is rather connected to the parent chain and is named as a substituent, it's called phenyl. So again, we use the YL suffix to indicate that it's a substituent rather than part of the parent. But it's not benzyl, it's phenyl. Benzyl is something else. So let's imagine we had 2, 4, 6, 8 carbons here. And maybe I have something bonded on carbon 3. So if I had 8 carbons in my parent, that'd be octane. If I put a benzene ring here, that would be 3-phenyl octane. If I wanted to call that 3-benzyl octane, I'd have to put a benzyl group there. And a benzyl group isn't just a benzene, it's actually an additional carbon connected to a benzene. So this is the benzyl carbon. So definitely try to remember the difference between a benzyl and a phenyl so you don't get them mixed up, because that's a common mistake that sometimes students make. So this phenyl ring sometimes will be abbreviated PH for phenyl, or you might see this Greek phi symbol representing kind of the circular nature of that ring. I don't really use that very often, so you won't You shouldn't probably expect me to draw it that way. I'd be much more likely to draw it as a pH or to just draw out the ring so you know that it's a phenyl ring. So we haven't talked about ketones, but this is a ketone and it would be called cyclopentadienone. So that would be this parent. So at the only carbons where there could be a substituent, which would be carbons 2, 3, 4, and 5, I could call that 2, 3, 4, 5 tetraphenyl. Or I don't need those numbers because there's only 4 possible positions where those phenyl groups could be without breaking noble gas configuration. So that would be called tetraphenyl because there are 4 phenols. There's also something called xylene, which is kind of a cool name. Xylene refers to a benzene ring with 2 methyl groups. So the 2 methyl groups could be on adjacent carbons. That's what ortho means. Orthoxylene is where the 2 methyls of the xylene are on adjacent carbons. That could also be called 1,2-dimethylbenzene. If they're on carbons 1 and 3, that's called meta. That'd be 1,3-dimethylbenzene. So metaxylene and 1,3-dimethylbenzene are the same thing. And if they're on opposite sides of the ring, that's called para. So this could be called paraxylene or 1,4-dimethylbenzene. So if you use xylene as the parent name, that includes the methyl groups. But since there are different constitutional isomers of benzene that have 2 methyl groups, you would at least have to indicate which 2 carbons those 2 methyl groups are connected to if you were going to name it as xylene. So if you're going to use the IUPAC system that we learned last semester and have been refocusing on every time we talk about a new functional group, to apply that to aromatic compounds, what you'd want to do first is to look for one of these situations here. Is your benzene ring connected to one of these 8 functional groups? If it is, you don't want to call the parent name benzene. You want to call the parent name whatever name corresponds to the benzene ring connected to that functional group. So over here, if we were going to name this one, we have an OH directly connected to the benzene ring. So I would look back here and say, okay, when OH is directly connected to the benzene ring, that's called phenol. So that means this in red is the parent, and it's called phenol. If I use this as my parent and call it phenol, which I should, that means this has to be carbon 1, no matter what. Phenol implies there's an OH bonded to carbon 1 of a benzene ring. And then I can number when whichever way gives the other substituents the lowest number. And that wouldn't matter since they're equally positioned at the same distance from carbon 1. So that would be called 3,5-dibromo, because there are 2 bromos on that phenol parent compound. All right, let's look at these examples here. Here, what I'm seeing is a benzene ring. When I see a benzene ring, I want to look at the things that are attached to it. If either of those things appear on this slide here, I don't want to call the parent benzene. I want to call it whatever one of these things is. So this is what I have here. C double bond OH. C double bond OH connected right there. So that means this whole thing I want to call benzaldehyde. That name is the parent name. It includes the ring and the aldehyde group, and it implies that the aldehyde group has to be on carbon 1. This is not carbon 1. Benzaldehyde requires that the aldehyde group be on carbon 1. And so I have to count around here, and then I get a 4-chloro. So 4-chlorobenzaldehyde would be the name of that structure. Here, again, I have a benzene ring. I look for the groups attached to it. I check the slide. When I've got a methyl attached to a benzene ring, that's called toluene. And again, that requires the carbon of the ring that the methyl group's on to be carbon 1. So I would call that whole part of this toluene. And that has to be carbon 1. So I want a number to give the bromine the lowest number I can, and that would be 3-bromotoluene. Likewise, when I have a methoxy group on the ring, that becomes apparent. That's called anisole. And here, again, if it's anisole, the word anisole implies you have a benzene ring with an OCH3 on it, and that has to be on carbon 1. And so I would obviously number this way to give the nitro group the lowest number I could. Nitro anisole. So here were the first 2 quiz questions. There were naming questions. And we would do the same thing. So it's not shown here, but clearly if this line ends here, there's a carbon, and it needs as many hydrogens as is required to complete its noble gas configuration. So this methyl group connected to the benzene ring is toluene. So my parent is toluene, and that requires me to start numbering here. And because it's symmetrical and toward the right or the left, I can number in either direction as I go around. So I get 2, 4, 6. And there are 3 nitro groups, so tri-nitro toluene. And this can also be abbreviated TNT. It's an explosive compound. 2,4,6 trinitrotoluene. Over here, if you're not seeing it, we've got ethyl groups, we've got nitro group, and we have an NH2. So if any one of those ethyl, nitro, or NH2s are over here, okay, here I see it. I've got an NH2 bonded to a ring. So that means that one should be called aniline. So the ring and the NH2 are all part of the parent chain, and that's called aniline. And because the NH2 is part of that parent name, the carbon it's bonded to has to be carbon 1. And again, it's symmetrical, so I can move around in either direction. So I've got 2 ethyl groups, 1 on 3 and 1 on 5, so it'd be 3,5-diethyl. And I've got a nitro on 4. So alphabetically, the E of the ethyl comes before the N of the nitro. So it'd be 3,5-diethyl 4-nitroaniline. All right, so let's talk about the structure of benzene, and we're going to get into this and continue it on Wednesday. We've been talking about conjugated systems, so this is an extension of that idea. Obviously, as we were saying, each one of these carbons is sp2. There's p orbitals on each one, and they're all overlapping with each other on top, and they're all overlapping with each other on the bottom. And so that creates the opportunity for molecular orbitals as a result from that overlap. So the first person to propose this idea of the structure of benzene being a 6-membered ring with alternating double and single bonds was Auguste Kekule, and his idea was incorrect. He thought it would be an equilibrium. The idea of resonance did not exist at the time. So we know it's not an equilibrium, we know it's resonance. So we've learned a lot since the 1800s, especially in chemistry. So much. So we know that the electrons don't just sit there as localized pairs of electrons between atoms and then once in a while maybe shift back to the other side. We know that the electrons are instantly in a molecular orbital that covers all 6 atoms due to the overlapping p orbitals side by side all the way around, right? So it's not an equilibrium. where it's shifting back and forth. Just to remind you what resonance is. Resonance is a situation where the electrons, even though we draw them localized in here, aren't. They're all over all 6 carbons in one or another of the molecular orbitals created by the atomic orbitals overlapping. So if there are 6 atomic orbitals overlapping, there should be 6 molecular orbitals. 6 atomic p orbitals will disappear and create 6 new molecular orbitals with varying amounts of nodes and stability. Sometimes you'll see the benzene written like this. Obviously, this arrow means resonance. Oops. Resonance. You might see it looking like this, right? When we draw the resonance hybrid, often we use a dotted line to show the electrons that are in resonance. So that's also a reasonable way to show benzene. This is also a common way to show it. Sometimes it just, instead of the dotted line, they'll just make a circle in the middle to represent that cloud of electrons that's in resonance. Depending on the situation, you may want to show that as a circle to indicate the resonance, or you may want to show the electrons this way. If the benzene ring is going to undergo a reaction that involves the pi bonds, where maybe one of these pi bonds comes out here and picks up an electrophile, which would create an intermediate that would look like this, and now I have a resonance stabilized carbocation, which obviously is not super unstable compared to other things we've seen occur. That's something we're going to talk more about in chapter 19, but just wanted to point out, we usually show the benzene ring with the pi bonds localized because that allows us to start showing how those pi bonds might move around to create reactions. So really the circle or the dotted line circle is probably a better representation of what the electrons are actually doing because they're not localized in these pi systems, but drawing the pi bonds in does help us to see how the electrons might move if they were going to react. So there's a couple different ways you could see benzene drawn. So let's talk about the stability of benzene. Benzene is, from one point of view, you could think of it as 3 alkenes in a ring. Why would those 3 alkenes be any different from 1 alkene? Well, the resonance makes them way more stable, and the molecular orbitals they're in, due to that resonance, make them way more stable, right? So if we think about a standard alkene, where the p orbitals overlap above and below the plane, as we said, the pi electrons are not that stable because they're not very close to the space between the nuclei. They're kind of above and below that space, right? There's a node splitting the 2 halves or 2 lobes of a p orbital. So the pi electrons aren't the most stable, and we know there's tons of different addition reactions where you can convert the pi bonds into a sigma bond, and that's favorable or product favored because the stability of the pi bond or the sigma bond versus the pi bond. But if you stabilize the pi electrons by putting them in an aromatic ring, specifically if it's aromatic, the resonance associated with that aromatic ring and the molecular orbitals that stabilize those electrons really lower their energy a lot. And that means that there isn't enough energy to produce this reaction. So there's a kinetic and a thermodynamic argument here. So let's take a look at that. Just draw this reaction coordinate system here. So if we're looking at the free energy, and we're just looking at this alkene versus the benzene, this pi bond is significantly less stable than the pi bonds here because of the resonance. So I'll call this B for benzene and this A for alkene. So from a kinetic point of view, since the alkene starts off higher in energy because it's not stabilized by resonance, it doesn't require a really strong collision to get the bromine to add across. So to get to that transition state, it doesn't require that much more energy than we already had, since we already started pretty high in energy. And converting the pi bonds to sigma bonds means the final energy is going to be significantly lower, because the sigma bonds are more stable than the pi bonds. So from a kinetic and thermodynamic perspective, this reaction is good. Kinetically, it works well because the activation energy isn't too high. Thermodynamically, it works well because the products are lower energy than the reactants. And I get a negative delta G. However, when I start with benzene, it's no longer kinetically easy to do the reaction because the benzene starts lower in energy. To get up to the transition state, it takes a significantly higher activation energy. So very few of the collisions that occur would have the energy. But that really just means it's not going to happen very often. So if the only problem were kinetic, then I could increase the temperature and make the collisions get this energy and get to the products. But there's also a thermodynamic issue, and I'm drawing all over this, and I'm realizing it's looking cluttered. So I'm going to just focus in on the benzene here. Thermodynamically, if I break this pi bond and imagine what would the product look like if I converted that pi bond into sigma bonds. Normally breaking a pi bond and producing a sigma bond makes it more stable. But this is a rare, very rare exception to that. This pi bond is stabilized by an aromatic resonance, which is a special kind of resonance because it's in a ring and it creates an especially stable molecular orbital. If I break that, and I don't have conjugation all the way around the ring, then I only have molecular orbitals or p orbitals extending part of the way around the ring. I can't make the specially stable molecular orbital that results from full constructive interference all the way around the ring. So when I have the aromatic ring and I make a molecular orbital resulting from full constructive interference all the way around the top and all the way around the bottom, that actually makes it more stable. And so breaking that, converting the pi bond into the sigma bond is actually an endothermic process. So it has a high activation energy, which is a problem kinetically, but even more importantly, it's not a product favored reaction to add across the pi bond of a benzene ring. Adding across the pi bond does convert a pi bond into a sigma bond, which in general is good, but not this pi bond because it's in conjugation and it creates an extra stable molecular orbital, which we're about to see in a minute here. So here's how to quantify that. So I'm just telling you this, and you're probably like, well, I don't know if I believe you or not. And that's fine, you don't have to believe me. But you can do an experiment that verifies it. And just like we were talking about early in the semester, looking at the stability of alkenes, by looking at hydrogenating them, we can do the same thing with benzene. So typical alkene, converting the pi bond into sigma bonds, where I add hydrogens across there, adding hydrogens across that pi bond to make sigma bonds, it releases energy because the sigma bonds are lower in potential energy or more stable than the pi bond. If I have to do it twice, it's an even larger amount of energy, right? Adding across one pi bond releases some energy, adding across the other releases a little bit more energy. So the total amount of energy is greater for two pi bonds than one. And so if I just were following this trend and expecting the third pi bond to be the same, then I would expect adding across one pi bond release some energy, adding across the other, converting that into sigma bonds would release more. Breaking the pi bond requires energy to be absorbed, but when the new sigma bonds are formed, even more energy would be released. So I would expect a larger increase, a larger release of energy because of the bigger difference between the energy of a pi bond and a sig bond. If I have three of them, it should be like 3 times the amount of energy, but it's not. It's actually less energy released to hydrogenate these pi bonds than it is to hydrogenate 2 pi bonds. And that's because the third pi bond is special. As we were just saying on the last slide, it provides full conjugation all the way around the ring. It creates molecular orbitals that would not otherwise exist if any one of these carbons in the ring is sp3. So if you want to convert one pi bond into sigma bonds with hydrogens by hydrogenating this one, then you have to go from this level up to this level. You have to go from 208, this is how much energy would be released, but you have to go up from a level that's 208 kilojoules above cyclohexane to a level that's 232 kilojoules above cyclohexane. So that's the equivalent of 24 kilojoules per mole higher in energy. So that's what we were just saying. It's endothermic. To break this pi bond and form sigma bonds, you have to put in about 24 kilojoules per mole to do that. Positive. Right? This is the only example we've seen where breaking a pi bond and converting into a sig bond makes it less stable. And that's because this pi bond makes it especially stable all the way around the ring, because now it's fully conjugated. As soon as I break one of the 3 pi bonds, it's no longer fully conjugated. And that extra stability of the resonance and the molecular orbital that involves full constructive interference all the way across the top and the bottom is gone once that pi bond is converted into a sigma bond. And so there's a slight increase in the amount of energy, or it's less stable with the sigma bond than with the pi bond when that pi bond makes the ring aromatic. So we can say adding in the third pi bond, since it actually goes down in energy because it makes it a little bit more stable, versus going up in energy, if I had to break 3 pi bonds that weren't in conjugation, it would take about 360 kilojoules per mole would be released into the surroundings. But really, to break these 3 pi bonds, only 208 kilojoules per mole is released into the surroundings. So the difference there is what we think of as the aromatic stability. If there were no conjugation and no resonance, it'd be about 152 kilojoules per mole less stable than it really is. And so that is an experimental verification of how stable benzene is. And that's the first part of this second quiz question. So the second quiz question, where I ask you to explain how aromaticity is stabilizing and how we know that experimentally, that's this. Experimentally, you can measure the amount of energy released when the pi bonds are converted to sigma bonds. And it's about 152 kilojoules per mole less than it would be if there wasn't any special stability associated with the conjugation, the resonance, or the aromatic ring creating molecular orbitals. So that's the experimental verification using heats of hydrogenation, measuring the energy difference when the alkene is converted into an alkane by adding hydrogens across it. And you find with benzene, the first one actually is endothermic, and then the next 2 would release some energy, but way less energy than would be expected if there were no special stability. So that difference in energy tells you about the stability experimentally of aromaticity in general, more specifically for benzene. So the theory behind that, the explanation, which is the second part of the quiz question, how does the molecular orbital theory rationalize that stabilization? Well, that explanation is here. All right, so we're saying there are 1, 2, 3, 4, 5, 6 carbons in the ring. Each carbon has an atomic p orbital on it to overlap side by side with the others. So if there are 6 of those orbitals, I need 1, 2, 3, 4, 5, 6 new molecular orbitals. In these molecular orbitals, I don't expect you to know their exact shapes or how many nodes they have exactly. It's kind of a difficult thing to predict because normally when we overlap atomic orbitals, the molecular orbitals that result are all at different energies, each one having one node more than the others. But this is an exception to that. In this situation, there's one that's especially stable. This is the key one. This one is so low in energy. Look at it. The pi electrons have full constructive interference on the top and on underneath the ring where the bottom parts of the p orbitals overlap. And that electron density is all over this area, and it's all over the area on the bottom. Kind of looks like a hamburger, right? These two parts are like the bun and the carbon atoms are like the meat. But that electron density is really spread out effectively over all 6 of those carbons, and those electrons are especially stabilizing. That's what I lose if I lose one of the pi bonds. If I convert benzene into 1,3, I was thinking about the name instead of drawing it. If I convert that into 1,3 cyclohexadiene, and I lose that pi bond, I no longer have p orbitals all the way around, and this orbital is gone. So this orbital only stabilizes 2 electrons, but it really stabilizes them and allows the whole structure to be much more stable than it would otherwise be. Also, the next 2 lowest energy orbitals are also relatively stable, and they're also equal in energy. So I really am able to stabilize 6 pairs of electrons in a way that would not be possible if I broke any one of those pi bonds and lost the full conjugation all the way around the ring. So as I said, I don't expect you to predict where the nodes are or the shapes of these. Those are determined based on some mathematical calculations. And those mathematical calculations have to match the experimental energy differences, which they do. So that's why we feel confident in their existence. And as we were saying, the 6 pi electrons exist in 3 bonding molecular orbitals. Right? These are the bonding molecular orbitals. This one is especially stabilizing for 2 of the electrons. The other ones have a node where the electrons are split on either side of that node, but they're still able to attract to multiple nuclei at once. So those are still lower in energy than they would be if there wasn't any overlap. And none of the electrons have to go in any of the unstable anti-bonding molecular orbitals. And so that really creates a lot of stability for benzene. And that's why when we talked about alkenes so far last semester and a lot again this semester, we said, if you have an alkene, you can do addition reactions across that. You can do a hydration, halogenation, hydrogenation, hydrohalogenation, halohydrin formation. There's tons of different reactions, Markovnikov, anti-Markovnikov, where things add across those pi bonds, because the pi bonds, when they're converted to sigma bonds, make it more stable. But that's not true for benzene, as we just saw. Converting one of the pi bonds into sigma bonds actually makes it less stable for the first one of those pi bonds that you do that to. So benzene won't really undergo addition reactions unless you have really harsh conditions and you can add across all the pi bonds, because as we said over here, when you add across all the pi bonds, you are able to make it more stable, and so that would be favorable thermodynamically to do that. But the first one also requires a lot of activation energy, so it's still a slow process, requires a large amount of pressure or temperature to get the collision strong enough. So kinetically it's difficult, and thermodynamically, especially if you're just trying to add across one pi bond, you can't, it's not favored thermodynamically. So as we're going to see in the next few lectures, because these are so stable, they don't undergo the same types of addition reactions we've been seeing all along. There's going to be a whole different type of reaction conditions that those undergo, which we'll obviously see later. So I ended a little bit early today, which is good. Makes up for some of the other days where I take a little too long. And there's definitely, some bullet points you want to be prepared for. So have an exam on this content next week. Practice up some of the Sigmatropic and UV-vis stuff from 17, and then some of the naming and conceptual stuff from chapter 18. And then on Wednesday, we'll talk more about what makes a ring aromatic, because there's more criteria than we've talked about so far. And we'll talk about some reactions that occur at the carbon just outside the aromatic ring. Right, we said benzyl. A benzyl group has an extra carbon bonded to maybe a parent chain or something, but this is the benzyl carbon. So having the ring there affects not just the ability to add across the pi bond or reactions that happen to the ring that we're going to talk about in chapter 19, but also the reactivity at the carbon just outside the ring. So we're going to talk about that a little bit on Wednesday as well. So we will get into more chapters, more sections from chapter 18. And so you want to be prepared for that as well for Wednesday. Any questions about anything? I appreciate those of you who were able to make it, and see everyone else later. Bye.